Oh, yeah.
No, that we don't, that's the document. Oh, I see. Hang on, I'll, so we want to set the camera. Probably. Oh, yeah. Now we're bringing. Working technology, remind me, Candace, we switch. Okay.
That goes up.
All right, hello everybody. Welcome to Geometry of Data. This is cross-listed Computer Science 6501, ECE 6501. Hopefully everybody's in the right place. I'm Tom Fletcher. I'm one of the instructors. I have Aman Srivastavas, our also instructor for this semester. We're going to be roughly sharing 50-50 lectures and all the things like office hours and grading and so forth. So that's the instructor plan. So today we're just going to go through the usual kind of course logistics. I'll try to go through this really quickly. And then I have my motivational speech, why you should be in this class and what kind of things we're going to learn, what to look forward to, which we're going to tag team today. I'll do the first part of it, and then Aman's going to do the second part of the introductory lecture. After that, we'll probably alternate topic to topic. Like every couple of classes, we'll switch back and forth. We won't do the same lecture back and forth like this usually. Okay, so yeah, so if you haven't found it already, well, hopefully, first of all, I should say the course on Canvas. Hopefully, you've seen this in your Canvas, whatever you want to call it, web page. If you're enrolled in the class, then you should be there. And if you go to Canvas, there's a link in the front now to this GitHub pages for the course. This is kind of our main web page where you'll find everything you need. And we use Canvas for doing things like submitting homeworks, basically. And I'll send announcements through Canvas to the whole class by email, and that kind of thing. But most of the material and things you need will be here on this GitHub page. By the way, of course, people that are on Zoom right now know we are streaming on Zoom. It's also being recorded and saved if you want to watch a course lecture after the fact. If you miss class or something, you can go find these on Canvas under the online meeting. You can either watch live or you can watch the recording later. It usually takes an hour or two for the recordings to come up, so you have to be patient after class is over. Let's see, but yeah, what I was going to say is people on Zoom, hopefully you can hear me. If you have any questions or anything on Zoom, just feel free to unmute yourself and blurt it out. It's too hard for me to see while I'm up here talking to see like your hand being raised or a chat. Just feel free to blurt out anything as if you were here in class and raising your hand, blurt out something. Don't be shy to interrupt if you need to ask the question. Okay, let's see. So, right. So the logistics, if you go to this webpage, there's just, we're here at this time. This is me, this is Aman, and our email addresses. The one thing people always ask is what are the prerequisites? There's no official prerequisites, like you don't have official courses you have to have taken to get into here. But I am going to assume throughout the semester that you have a basic understanding, that means like at the undergraduate introductory course level, of probability, linear algebra, multivariate calculus, and that you're comfortable in Python, programming in Python. Okay, you don't have to be a expert hacker, but just have basic programming abilities and in Python. Now, maybe you haven't taken classes in all of these things, and that's okay, as long as you feel confident that you know that material fairly well, again, at the introductory level. Or if you're a risk taker and say, I've never done any linear algebra, but I'm gonna, maybe pick it up as I go. That's possible also if you're comfortable learning things on the fly. But that's kind of the basic understanding of material that we were expecting throughout the semester. We're going to do all of our homework assignments in Jupyter as Jupyter notebooks. If you're not familiar with Jupyter, that's okay also. But it's one of these things you'll have to pick up as we go. There's no official textbook for the course. I have a couple books if you're interested in reading more about manifold geometry, which is a big part of the course. The mathematics of the course will be Riemannian geometry or manifold geometry. And this is a physical hard copy book that you can find in places called libraries probably, or bookstores, I don't know. And this is some notes that you can find for free on the web. But they're, again, optional reading, not required. If you haven't done Jupyter before, I have a few. These are just little notebooks that I put together for my undergraduate course. One is like a math guide of like how to type math, and it's really LaTeX. But this is the kind of things when you're answering math problems, you have to type math notation. So there's a little bit of a guide here on how to do that. I guess it's a notebook I want to open, but yeah, you can use these if you're interested in some Jupyter notebooks for help. The main thing you'll want to refer to on this page is the schedule. That's where all the details will be. It's mostly blank right now. But there'll be the topic. Sometimes there'll be slides. Actually, very rarely. A lot of our lectures will be on the Blackboard. Like today, there's slides, but sometimes there will be, sometimes there won't be. They'll be linked always. Any slides will be posted on the web. And then there'll be potentially reading, not always. So again, today, no reading. The first reading will start later in the week. You can get started now if you want, but these are some notes that I have on Riemannian geometry that, fairly short notes. It's not a full textbook or anything, but everything you need to know about Riemannian geometry are in the notes, but you can find other material elsewhere as well. Then any homeworks we have, and we're thinking there will be 4 homeworks throughout the semester. They'll be posted as PDFs here, and then the due dates will be kind of posted there as well when you want to turn them in. This is the syllabus, meaning just a list of topics that we're going to go over, which I won't go through one by one right now because we have an introductory slides that'll go through kind of some of these things, but we can look over those there. And then the logistics of all the, the fine print of like what all the policies for the course will be. And yeah, a lot of this is kind of boilerplate, so I won't read it, line by line or anything like that. I'm just gonna make this a little bit bigger. The main thing on attendance is I would encourage you to be here in person as much as possible if you are taking the course in person, which is most of you. If you have to do online for any reason, you're welcome to just do it online. And you're also encouraged if you're sick to go do it online and not come into class and get everyone else sick. So feel free to take advantage of the virtual attendance for any reason. You don't have to tell me that you're going to be virtual. I don't and you're not going to be penalized for not being here in person. So don't feel like you have to come in person if it's not working for you. let's see. We're gonna have office hours. We haven't set those yet, but both Amon and me will have office hours. And so, you know, you can come see us in our office hours. You can ask us questions by email. We have Piazza set up through Canvas. If you go to there, I really encourage everyone to use Piazza and ask your questions publicly so everyone can see answers. You can be anonymous if you're kind of shy, don't want your name attached to it. But if you do have the questions on Piazza is the best way to ask questions so that we can answer and everyone can hear the answer or see the answer. What I'm saying. And definitely encourage in-class participation. So a lot of the material in this class is a little bit meant to be thought-provoking and not just like rigorously dry and boring, like here's an algorithm, here's how you do it, but more like a high-level conceptual thing that we need to discuss. So for instance, we're going to talk about topology, topology that your data lives in. And these might be things that you haven't really thought of before as a student or as someone who has maybe done machine learning before. And so, you know, to help you get through thinking through these types of things, like what's the topology of the data space my data live in, it helps to ask a question and then I'll, you know, we can have a discussion about these types of things. So definitely speak up, ask questions, and don't be shy to interrupt. Let's see, announcements will be, like I said, I need to do a find and replace Colab with Canvas. This should be Canvas and not Colab. I changed it in a couple of places, but apparently I missed these two. Yeah, so Canvas, I assume I can do it in Canvas. I've only done it in Colab. I assume there's the same function in Canvas. I'll send, you know, spam the class kind of emails. And so, yeah, so make sure you have your email set up the way you want to receive emails from the course. They should be emails that you see, or if they're time sensitive, like, okay, there's a typo in the homework that you need to know before it's due. You want to be able to get their emails. The course grades, basically the thing to note here is that we're doing homeworks only, and then a final project at the end. So there's no in-class written exams or quizzes or anything like that. It's all take home. You've got a long time to do things. I have misspelled homeworks. It's not homeworks, it's homeworks. Yeah, so you'll notice that 4 homeworks are worth 3%, and the final project is worth 20%. It's actually equal to 1 homework. And so you can kind of, as you do the homeworks, we kind of get a sense of how much work we're kind of thinking the final project will be. The final project will be a group project, so you'll work in small teams, say 2, 3, 4 people or so. And it's open-ended in the sense that I'm not going to tell you, or we're not going to tell you what to do. You're going to kind of come up with ideas on your own, given what you learned in the class. It has to do something with geometry, something with data. That's the rule, basically. And so, yeah, so we'll talk more about details of like, and we'll help you with ideas as we get to the middle part of the course. And yeah, like I said, everything's a Jupyter notebook, and it's going to be things like written answers combined with code and experiments you run, combined with math. If you have to type up answers to math problems, equations, and things like that will be part of it as well. Homeworks are due 1 minute before midnight on the due date through Canvas. And I do have a late policy that if you're up to 24 hours late, you'll receive 10% off. If you're between 24 and 48 hours late, so 2 days late, you get 20% off. And anything on 48 hours is just not accepted. So you have this kind of buffer if you are willing to lose points. I'll say, like, you know, everyone has from time to time extenuating circumstances, especially grad students. If you have like conferences you have to go to for your research, if you're doing research, or other UDA sanctioned events you have to attend, and you want, you know, you need another, you know, few days to finish your homework, let me know in advance. Or if you get sick and have a serious illness or problem, that any reason that you think you need an extension, please let me know as soon as you know and in advance, and obviously we'll accommodate things as they come up. Almost done with the logistics. The last main thing of the logistics I need to cover is the policy on what is considered working together and totally fine, what's considered cheating and not okay. Where's that line? So basically, the class is meant to you know, be again thought-provoking, and discussions are always welcome. And so that includes when you're working on homeworks, you can discuss it with your classmates, maybe even work out problems on like scratch paper or on the board in, you know, a space somewhere. What you're not allowed to do is copy someone else's assignment, or share your written up assignment, final assignments, let's say, with a friend and let them copy it. You need to really write up the assignment on your own. The final project's different, of course, because you're working in a team and you write it up jointly together. So that's really the line. You're allowed to discuss concepts and tackle problems together, but then when it's time to write it up, what you're going to turn in, write it up as an individual on your own. Okay. You can use online sources. So you can Google things like, I want to know about the stereographic projection. You Google that, you find a Wikipedia page for it. It has equations on it. You can read the equations and then implement them in Python. This kind of thing, all okay. Anything you do that to find an external source that's not one of the reading material already for the class, you should cite it in your homework when you submit your homework. So if you use the Wikipedia page for stereographic projections, just add that as a citation. I use this web page in my working on homework. Now the big one that is, you know, the hot topic of the day is ChatGPT and other related AI, generative AI, chatbots, and so forth. Those, mainly ChatGPT, are also permitted, allowed, so you can use AI with the following caveats. We're going to treat it just like any other internet source you would use, which means that you should not just copy it verbatim. So I can't type into ChatGPT, hey, ChatGPT, do my homework, and then cut and paste the answer that ChatGPT gives into a Jupyter notebook. You can ask it, you know, prompts and questions about what you're working on, and read what it comes up with, but digest it, think about it. You know, it may be wrong. That's one of the dangers. And then write it up again, write it up your solution yourself. Don't just, again, cut and paste it. And again, as I said for other online sources, please cite, I use ChatGPT. And in addition to saying just, I use ChatGPT, please give us, as part of the citation, the prompt that you typed into ChatGPT. Now, very often, as you all know, I'm sure by now, ChatGPT can be like a discussion with like 50 prompts back and forth, right? But just at least give us the key prompts, maybe the final prompt that you ended with that gave you the key, like, kind of insight that you needed. You don't have to give us the whole discussion, is the point. But the key prompts. And yeah, so the final piece of advice or recommendation I give here is that, yes, we're allowing AI, but I would say use it sparingly. And don't run to ChatGPT at the first, you know, as you start the homework. Try the homework on your own, think about it on your own. You'll learn the material better if you struggle with it a little bit, and go to ChatGPT for, you know, pieces here and there or places where you get stuck. That would be our advice. You know, use AI to enhance your learning, not to do the homework for you. Okay, so that's kind of our policy on AI. I mean, I'll pause here and ask if anyone has any questions about this or any other thing on the course logistics so far. Yeah.
I had a quick question on the readings.
Yes.
So for the day that the reading is aligned with, are we expected to read it before class that day or read it for the following class?
Good question. Yeah. I'm intentionally vague on that in the sense that I don't have a recommendation one way or the other. Typically the class will be talking about things that are in that slot. So like, let me go back. Oh boy, something with the new Windows maybe does things differently than I'm expecting. Hold on. No, it's a wrong key. Okay, yeah, sorry. So for Thursday, the Riemannian geometry notes are section 1 are the reading, and topology basics is exactly what that topic section 1 is about, is topology. So if you want to read before class, you're absolutely welcome to. That's why we'll post it in advance, but you're not required to. So you can show up to class and be like, hey, surprise me. You know, I don't know anything about topology, and we'll just start and you can read it after class. It's whatever works best for you and your learning. So yeah, either way works. I know students do it both ways and it works just fine.
Thank you.
Any other questions on anything so far? Okay, I think that's the rest of the policies are I will admit to plagiarizing. You shouldn't plagiarize, but I did plagiarize the rest of these policies in the sense that these are boilerplate things that, you know, School of Engineering, you might see exactly the same verbiage in other courses if you're in these other courses. But anyway, there's various things. Obviously, if you have a disability or other learning need and you go through SPAC, come talk to me about that, and we'll accommodate you, work together on a plan for that. Obviously, again, we don't discriminate based on religion, and there's some resources if you have anything sort of religious accommodations or things that you need help with. We don't tolerate any forms of harassment, discrimination, violence, of course. Don't be violent. There's a lot of resources from the university for those types of things. Again, if you have any concerns, I'd be happy to help you, but also take advantage of the university resources. Let's see. And then there is some health, well-being, mental health resources, student support teams, diversity, community, and identity support. All of these things, again, are resources that you're not familiar with and you think you could take advantage of. Absolutely, here's some links for all of that stuff. Let's see, I think that's everything on the policies and logistics. Any questions? Okay. Then with no further ado, I'll start the motivational speech, which I will start. And if I can avoid talking for too long, Aman will finish. We may bleed over into Thursday with the introductory stuff. Okay, so yeah, so this is geometry of data. And what I want to start with is a little motivating example. And this is mainly not even a very realistic example, but it's a data set that is popular in computer vision and machine learning for classification problems. There's this data set called CIFAR 10. It's 10 classes of images, and it's not a realistic data set in the sense that they're very teeny tiny images. They're just 32 by 32 pixels. By 3 means 3 color channels, RGB. So you multiply all these different degrees of freedom together, and there's basically 3,000, not basically, there is 3,072 dimensions total to represent one image here, okay? And so this is, again, like a standard simple data set. Most really realistic data sets, like even if I take a picture of my camera on my phone, right, is going to be millions and millions of pixels times 3 color channels. And so it's in the millions of dimensions to represent, you know, meaning I need a list of 1 million numbers to uniquely represent an image like on my phone. But we'll just use this example of CIFAR 10 because it's a nicely simple and available data set. And it's very small in terms of real world, but it's 3,000 is still a lot of dimensions. So I can imagine generating CIFAR-10-like images randomly. And by randomly here, I mean uniformly randomly. So I pick every one of those 3,072 numbers as a random number uniformly between 0 and 1. And I can put that together into an image and display it. It would look something like this. Okay, so this is a uniformly random generated image. I did it myself, so I know it's uniformly random. And I can keep doing this, and I never get anything that looks like a real image. Except every now and then, once in a blue moon, I randomly generate something that looks like this. And of course, I'm just kidding. This is one of the real images. I did not randomly generate this one. So the point is, you know, that I can generate images until the end of time, and I'll never accidentally randomly generate an image that looks like this dog image, okay, which came from the real CIFAR data. And why is that? Why? Maybe I'll pause and ask the audience here. Why is it the case that every time I generate a random image, I get gibberish and I never see something in the image? I don't see, it's not like clouds where you can say, oh, that looks like a house or something. It doesn't matter how many times I do this, I'm never going to get something where I actually say, oh, that looks like there's something in this image. There's a dog, or there's a airplane or something. Why don't I ever get something that looks like something when I generate data from it? Yeah.
Pictures like that exist in a lower dimensional space than we're searching through.
Yeah, exactly. So these pictures that we're seeing here don't exist. Real data does not exist in the ambient representation, ambient meaning the kind of original representation that I'm representing, the full 3,000 dimensional space that this data is coming from. These random images are filling up that full 3,000 dimensional space. These images live on a much lower dimensional space than that 3,000 dimensional space. And so why does living on a lower dimensional space make it really difficult, and I would say actually zero probability, to get the dog image randomly? Why would lower dimensional space cause? I'm going to dig into the back there.
It's probability 0 to hit a lower dimensional hyperplane.
Right. Yeah. So if you think about taking a plane and like throwing darts at it randomly, uniformly in a little box, if I had a line through that plane, that line, the area that line covers is zero area, right? So lower, if you drop down a dimension, then if you think of probability as area or hypervolume, if you're in high dimensions, a lower dimension has zero volume or zero area or zero probability. So anytime I drop down in dimension, I get something, probabilist, we call it measure zero space. So it's impossible, it's probability 0 that I'm going to hit it randomly. So yes, that's exactly what's going on. And maybe I'll dig in with one more level down into, okay, so let's think about, why is it the case, do you think, that real data lives on this lower dimensional space? Exactly. So what is it about this image, if we just think of like this image visually that's different from these images, that would cause it to have lower dimensions, lower kind of degrees of freedom of what possible images there are? If my question makes any sense. Yeah.
There are patterns in the images, like blocks where the color is the same.
Yeah, exactly. It's
less information.
really about, there are blobs, if you will, in the image where there's chunks of similar colors. And one way to think of that is if I look at a pixel, the pixels next to it, generally speaking, are correlated. Okay, they're not just independently random. If I'm a brown pixel here, next door to me is likely to be a brown pixel, higher probability to be a brown pixel. And of course, at edges, then you kind of, that changes. But if you're in the middle of one of these blocks of blobs, pixels neighboring you have some correlation to you, some relationship to you, and that loses degrees of freedom. They can't just be willy-nilly any value. They're somewhat constrained, and these constraints or correlations drop you down in degrees of freedom that you can change the image. So yes, that's what we're seeing here. And it's kind of the main principle that's going to be underlying the theme that's going to be underlying the entire class. When we talk about geometry of data, this is what we mean, is what is the geometry of the space that our data lives on, and how can we leverage that knowledge of that geometry to do better machine learning or statistics for data analysis. And so this is my poorly drawn cartoon of the story that we just saw, is that the 3072 dimensions are a really big giant hypercube of 3072 dimensions. And again, you think of the edges of this hypercube being 0 to 1 continuous values. And again, if I just throw random darts in here, I'll get one of these static images. And then imagine this gray bean shape with a handle I've drawn here is a lower than 3072 dimensional smooth surface, what we call a manifold. We use the letter M for manifold, and that's where my data really lives, is on this lower dimensional space. So now to talk about some of the topics that we'll be covering with that basic theme. I should mention that this is often known as what's called the manifold hypothesis. So you hear this in machine learning, the manifold hypothesis, or you'll hear people refer to the data manifold. And it's very hand wavy, very vague, but this general principle is that my data lives in a lower dimensional space. And we will talk about what it means to be a manifold and whether or not that's a valid assumption here for the real data. So one topic we'll talk about in this class is what's known as manifold learning. So if I believe my data lives on a lower dimensional manifold, one goal which is reasonable is to say, I want to learn what is that manifold. Because if I've just given you these CIFAR images, you don't know, what is the subspace that they live on? What dimension does it have? Does it look like a flat hyperplane? Does it look like a sphere? Does it look like some crazy manifold that's hard to describe? You just don't know. And so manifold learning is the process of trying to learn a representation, mathematical representation that gives you that data manifold. So yeah, what I just said, basically a model of that data manifold. So very often this will involve what we'll talk about in the next few days, learning what's called a coordinate chart. So you think of a map, and the coordinate from the map will take you to where you want to go on your data manifold. That looks like this. So if I have a flat map here, a chart, it maps non-linearly, potentially up to positions on my learned manifold. And I can move around the space of valid data, valid images in this case, by kind of moving around this chart. This is kind of a very simple toy example of some various manifold learning algorithms that are implemented in scikit-learn, which is a Python package. And a manifold is this, again, a toy S, kind of a curvy ribbon, if you will, in 3 dimensions, but the 2-dimensional manifold, the S itself only has 2 dimensions. And so if you imagine they kind of color from green to red, kind of color scheme there, you imagine I want to map that down to a nice flat representation where I can walk around where I want to be on the S, and really the intrinsic dimensions, which are just 2. So that's the kind of idea. And then it's a little bit small here, but a slightly less toy example is some handwritten digits, and then kind of, again, flattened out to be represented as best as possible in a 2-dimensional embedding. Okay, so carrying on with the theme of data living in high dimensions, another thing that we hope to kind of demonstrate as part of the course is that it's very difficult to work in high dimensions. Things in high dimensions, the geometry concepts we're very familiar with all the way back to being a kid, like triangles, geometry, kind of Euclidean geometry, right? Planar geometry, 3D geometry. None of our intuition that we're used to really carries over into high dimensions. And so the following example is just a taste of what goes, kind of weird in high dimensions. And so, again, we can think of this, for instance, as images. So think of, again, that CIFAR example, just a unit cube as the space of all possible images of a certain dimension. And so this d-dimensional unit cube, it means I go from, one corner at the origin 0, 0, 0, and then the opposite end of the unit cube is 1, 1, 1, 1, 1, right? So it's but you have to extend beyond. I'm obviously drawing just 2 dimensions, but think of this as being d dimensions, where d is a large number. And now the question is, first of all, let me start with, before this question, what is the volume, really the hypervolume, the d-dimensional volume of a unit hypercube? Yeah, it's 1. So if I go to, obviously I go area, it's width times height, that's 1. If I was 3 dimensionals, width times height times depth is 1. The sides are always 1. And you keep on going higher dimensions, I still have always like sides of length 1, and so I'm just multiplying by 1 every time. The total hypervolume, if you will, is 1 to the d power, which is just 1. Okay, so yeah, the original hypercube is hypervolume 1. Now, if I shrink the hypercube by epsilon, where epsilon is a very small number, let's say if our total length is 1, epsilon is just a lot smaller than relative to 1. Let's say I'm just going to shrink every side of the cube. You think every corner, every point coming in, every coordinate of every point coming in by epsilon. So if I do that, who can tell me what is the volume of the red hypercube now?
Minus 2 epsilon.
All right, maybe I'll get a hand raised because everybody says it gets muddled. Yeah.
Minus epsilon power d.
Yeah, that's right. 1 minus epsilon to the d power. Okay, and if d is something large,
That should be sure.
sorry, it should be 2 epsilon to the 1 minus 2 epsilon to the d. I think someone back there caught that. Then notice that this is a number less than 1. You can say it's 0.999999 as kind of close to 1 you want, but slightly less than 1. As you take d to infinity, as d goes higher and higher dimensions, like as you get to, say, the phone, megapixels, like d goes in the millions, that volume is 0, or very, very, very close to 0. So I'm just, because if you think of this in 3D or 2D or 3D, what we're used to, if I just shrunk the edges of a square a little bit, the red square is almost volume 1. But in higher dimensions, shrinking just a little bit, you go very quickly to 0 volume. And to just give you a concrete number, let's take a little bit bigger images than the CIFAR images, but let's add 256 by 256, still very small images. And my epsilon is going to be the smallest, if I have 8-bit color channels, right? The smallest number I can get is 1/256. That's the smallest color change I can make. So that's the smallest quantizable epsilon you can get in 8-bit images. And in that case, in that dimensionality, the volume of the hypercube shrunk by just the smallest amount you can make a pixel change is 2 times 10 to the minus 670. So you see that's pretty much 0. So what does that mean? It means if I were to randomly generate an image, it's guaranteed in this sense to be in this small margin, epsilon margin of the boundary. So every randomly, again, uniform, if I just think of this as a uniform random sampling of images, they're going to be with 100% probability in, on the edge, on the boundary of the hypercube. And they won't be in what we typically geometrically think should be the vast middle. It's not the vast middle. The middle is actually almost nothing. Yeah.
So when you say you're shrinking just a little, shouldn't there also be a limit of epsilon goes to 0? And then
well, no, because the epsilon proportional to the edge length, and the edge length is a fixed number 1. So I mean, yeah, we could play. Yeah, you're right. We can play games about limits and things, but I don't need to go. I mean, this d going to infinity is actually not necessary. I should have just said d is large.
it's hand waved a little. I mean, just
Yeah, but yeah. So, but it's a good point that like if I want to think of limits, I can think of like epsilon going to 0 and d going to infinity simultaneously. But here I want to think of epsilon being proportional to 0 to 1 in our case, and again, for images that are kind of quantized at a byte or so, I can make this different. I can have 16-bit images and maybe this is a different number, still would give me something very close to 0. And then this is again, a fairly low, or very small d actually for modern day images are actually way bigger than this d here. And this is just as an example that any relatively reasonable d and any relatively reasonable epsilon, and this is the smallest I can get, and for 8-bit images, it's going to give you 0 for realistic data. Yeah.
So some question, so for this case, the dimension is for the 256 squared times 3, right?
Yeah, the dimension here is 256 times 256 times 3. Yeah. So if you take, and maybe someone can double check it on a calculator, if you take epsilon 1 over 256, and you take this number as d and plug into that, you should get this very small number. Yeah. Okay, so somewhat counterintuitive. Again, we're working in really high dimensions, which is what we do in real data these days. A random probability, uniform probability is going to be on the edges. All your samples will land on the edges of your hypercube. Another example of some weird things. So that was volume behaving weirdly in high dimensions. We can also talk about other geometric concepts. For example, distance. So take 2 points. What's their distance? Okay, and so again, I'm going to use that unit d cubed, and now we're going to sample 2 points uniformly and say what's the distance between these 2 points. Okay, so I'm going to have another random variable. If x and y are random variables in the they're basically d-dimensional vectors. I'm going to compute just their difference and take the norm, the L2 distance between, or Euclidean distance between x and y. Okay, and let's look at how does this behave as I increase distance, or sorry, increase dimensionality. So at dimension 1, I'm on the unit interval. So if I pick 2 random points in the unit interval, notice this is doing this experiment, say like 1,000 times, and then plotting a histogram of all the d values, the distance values, d being capital D distance. If you have 2 random points on the interval, they tend to be close together. So it is the higher probability that they're going to be close to 0. They land close to each other. Very low probability that you're going to get one very close to 0, one very close to 1. So you won't get things that are almost 1. And you can see this is actually just a linear slope ramp here function and you can actually compute this probability distribution if you think about it carefully. If I go to d equals 2, so now I'm at a unit square in the plane, then notice this shifts a little bit so that now it's getting harder to get very close together. You're more likely to be somewhere in the middle, still maybe a little bit closer to 0 than close to 1, but like sort of centered here, a bump, if you will, and that's on a unit square. Notice that the max distance goes up, right? Because that could be at opposite corners of the square or square root of 2, like 1.4, whatever that is, apart from each other. Yeah, question.
What's the axis again?
The x-axis is distance between the 2 random points. The y-axis is the probability density. So if you notice, so it's normalized so that this histogram sums to 1. And by that, I mean, the area under the shaded blue should be summing to 1. So that's why it can be higher than 1, like 2 is fine, as long as it's like a probability density, not a probability itself. Okay. This number at the top I've put up here is just the mean of this distribution. So this distribution has a mean at 0.33 roughly, like somewhere like right here. Yes. Then next to the mean is shifted of this distribution, which has shifted up to 0.5, somewhere like in the middle. Okay. As I go higher now, I've skipped a few dimensions just to kind of save time here. I'm not going one by one. I go to d equals 10. You see that I get now again a kind of symmetric, more symmetric, I should say, hill You know, the scale has changed because now distances can get really large as you get 10 dimensions to move in. You can go up to square root of 10 here, or so. Okay, and so you can kind of see what's happening if I keep going. 100 dimensions, the distribution of distances look like this. 1,000 dimensions, and now 10,000 dimensions, I get something that looks like a delta spike. And of course, you have to take into account that, again, this is scaled every time the scale gets larger and larger, but the concentration of distances relative to, again, the max distance gets thinner and thinner down to a delta spike in the end as d goes to infinity. And so what's happening here, let's think about what does this mean? It means that if I sample in very high dimensions, and notice I've only gone to about 10,000. Again, we could go into the millions if very easily with modern data, but if you're to sample uniformly 2 data points, they're going to be equidistant from each other. I sample 3 points, I'm going to get basically equilateral triangle in my data space. 4 points, I get a tetrahedron with equilateral sides. I'm always going to be sort of the same distance, no matter what I do. So when we think of uniform sampling, we're thinking of either an interval or a square, and we think of, okay, it's distributed all throughout, but in high dimensions, things are actually have some structure to them. They're actually going to be equidistant from each other, sort of have this weird structure that forms. Okay. Any questions about those two examples? Okay, yeah, coming back to CIFAR, just to see what that last example does with real data. Well, we can take 2 random samples of this real data set. We know the dimensions, 3,000, and we can build a histogram of where the pairwise distances between 2 random real images compare it to what we just saw. And so if I do that, I take pairs of CIFAR images, I compute their distance, and then I build a histogram of all the distances that I come up with randomly selecting CIFAR pairs. I get this histogram. I compare that to the uniform distribution at 3,000 dimensions, and it looks a lot different. So notice, and now I've made the scales the same on the left and the right so that they're comparable, the 2 plots. Notice the uniform sampling, I get that delta spike kind of behavior where uniform samples are equidistant from each other. But in CIFAR, real images, there's this spread to the distribution of distances. And so what's happening here is, again, now because I went down to lower dimensions, I'm not really uniformly filling up the full 3,000 dimensions. I get away from this behavior because the intrinsic dimensionality of my real data is much lower. Okay, so the good news about weirdness in high dimensions is it's somewhat mitigated by the fact that our data don't really fill up all those high dimensions. So that the fact that they live in a lower dimensional space actually is a good thing. It's in the sense of the way the distributions behave. Okay, so that's a little bit about weirdness in high dimensions. The next thing, getting back to topics in the course. Another thing we're going to talk about is something called manifold valued data. So manifold learning, I started with, say, CIFAR images that live in a Euclidean space, but we know they live on some unknown low dimensional manifold. There's also the case where I actually know that my data lives on a known manifold. The values the data take are not Euclidean values already. They're represented from the get-go as values on a manifold. And when does this come up? So yeah, so I always like to say it's a known manifold. I know the manifold, I'm not having to learn it. When does this come up? This comes up when I have specific known constraints. They may be physical constraints or otherwise constraints that I can write down as an equation. They can be nonlinear constraints, and I can put them on my data. We'll give some examples here in a minute. If your data lives on a manifold, you know, because of nonlinear constraints, then the first principle is that you should not do linear data analysis on that data. So if your data lives on a sphere, you shouldn't try to do the mean of the data points, because adding points on a sphere will take you off the sphere. Okay, think about taking the North Pole and the South Pole and you average it, you'll get the point of the center of the sphere, which is off the sphere. And so you'll violate the natural constraints of your data. Your data is constrained to live on a sphere. Doing linear data analysis will take you off of that constraint surface. And so some examples. One example I like to give is just like geolocations, like locations on the Earth. I have data that's like a bunch of locations on the Earth. That's a very natural sphere, right? And I would only do linear statistics on that type of data, but more data that has directional, like sphere or circle representations would be like molecules. So molecules have orientations between the different atoms in the molecule protein. Robots have, you know, directions like self-driving cars, also have directions they're moving in and changing directions, turning and so forth, and controls for turning and so forth. And those are usually circular constraints. Yes, I already mentioned positions on the Earth. Motion capture, when you have a person or object that you're doing motion capture on, the joints are rotating, right? And so those are spherical or rotational data. The time is actually a directional data. So time lives on a circle, right? It goes 0 to 24 and wraps back around. Or the days of the week or the days of the year, what have you, everything is cyclical there. And so really time lives on a circle. If you really want to do time analysis as your input data, you can treat it as a circular data set. Here's an example of data that I work with in my research that is directional. So this is something called diffusion MRI, magnetic resonance imaging. What happens here is when we take a picture of the brain, this is really a 3D picture, by the way, I'm just slicing through it in one particular axis. Instead of getting just a number, like a gray value at every point in the 3D in the brain, we actually get a lot more information. We can get these little vectors of directionality. What that's telling us is the fibers, the axons in the brain, what direction they're headed in. And these directions are unit vectors. And so at every point I have a three-dimensional unit vector. So it's really lives on a two-sphere at every point. And so now my pixel values, if you will, are points and spheres. And I know that that's a constraint I have in this data set. And I should, do my machine learning or statistics of this data with that constraint kind of naturally in mind. And so thinking of it as a spherical data set. Okay, the last topic I think I have, and then I think we're going to have time to hand it over to Aman's slides here, is a type of known manifold called shape manifolds. And so this picture here is a cartoon of a manifold. Again, think high dimensional, like we had so far, high dimensional that my data lives on. And now I'm going to think of what if I wanted to represent shapes and shapes of objects. So you can think of like shape meaning if you have a two-dimensional photograph and I outline whatever object is in the image in that photograph, and I just want to understand what's the shape. What is it? Is this a person? Is this a cow? Is this a horse? What is this shape I see in an image? I'm going to represent shapes, and we're going to see the mathematics of how this works later in class as a point in a high-dimensional nonlinear manifold. And when we do data analysis on manifolds, we're going to see that the main ingredient I need is to be able to think about what is the distance on this manifold between two data points. So if I have this person shape and this bone shape, if you will, these are of course all just cartoons I drew, but imagine real data that looks like this, then I can compute somehow a shortest path between these 2 points on my manifold, and the distance tells me something about how similar or how different these two shapes are. And just that one tool, shortest paths, what are called geodesic curves, distance between points on manifold lets me, we will see, do lots of very sophisticated statistical analyses and machine learning of data that has natural constraints. So I can do things like average shapes. So this is a bunch of brain structures called the hippocampus. And then on the right there is an average of all these brain, these hippocampi. I can look at the variability of shapes. So this is a kidney, and there's a video here associated with it. When I say variability, I take the mean, and then I look at how does the mean vary across my population. And it's not on a loop, but let me see if I can get to loop. And so this is a movie of the main variability in this kidney data set, which basically is, you see the main variability is some people have tall, skinny kidneys, some people have short, fat kidneys. That's kind of the main variance you see in a population of kidneys. And why is knowing the variance of a data set important here? Well, if I wanted to use information about training a model, what does a kidney look like? To find it in a new, this is like in a CT image, I want to find a new kidney from an image I haven't seen before. Training it about what is the average kidney and what is the usual variability of kidney, what does the kidney look like? I need some kind of shape model of that. I'm a bird watcher, and so one of my favorite bird identification tasks, if you will, or challenges, is telling the difference between a crow and a raven. You can see both of these in the kind of Charlottesville area. Ravens are more likely to be in the mountains, or a little bit higher in the mountains usually, but you can see them here as well sometimes. Anyway, can anybody tell if you saw one flying over here, you saw these two birds flying over, can you tell the difference? What's the difference between the raven and the crow here?
Probably the tail.
Yeah, the tail. So yeah, so there's another difference, which is the raven's bigger, but the raven can also be higher in the sky and lower in the sky. It's hard to tell how big the bird is. But yes, the tail, this is kind of a square tail. Their tail always has a bit of a point to it, the raven. Now, of course, they can open their tails or close them a little bit, but it's still the case that this one will be kind of flattened or rounded at the end, and this will be a little bit pointy, like more diamond shaped at the end. And that's basically all you can go off of if it's flying overhead like that. So shape is very important, is the point, in identifying things. So if you tried to train a machine learning algorithm to tell the difference between an American crow and a common raven, it's not going to use color, it's not going to use texture, it's not going to use the background, what have you. The only thing it's going to be able to have to learn is the shape. And so yeah, so there's classification problems. I can classify objects. We can all do this visually ourselves. You can tell me what these objects are, you know, bird, butterfly, cat, cow. We all know what these are, even though there's no information here because I've gotten rid of everything except for the shape. Okay, and then I think, oh no, I'm going to do this one more slide. Okay, yeah, and then I'll give it to Aman. And I'm running over just a couple minutes. But really quickly, another topic in class is going to be something called information geometry. And what do we mean by this? So if I think of, I have a probability model, and that can be as simple as a Gaussian. I have parameters for that model. I have a mean and I have a standard deviation. Those are the parameters. I would fit those parameters to my data to say, what's the best Gaussian that fits my data? Or I could have a very complicated model, like say a deep convolutional neural network. It has millions and millions of weights. Those are the parameters of that model. And I still fit those parameters to my data set. So it doesn't matter what kind of data analysis you're doing, you almost always have a model, and it always has parameters. And in these cases, we can think of the parameters of our model also living on a manifold. So our data lives on manifolds, but also our model parameters can live on manifolds. And that is the topic of what's called information geometry. And just to give a very quick example before I stop talking here, if you think of just a two-dimensional Gaussian, a bivariate Gaussian, so you have a mean, which is a 2-vector, and you have a covariance matrix, which is a 2x2 matrix, we'll call it capital sigma. The covariance matrix has to be symmetric, and it has to be positive definite, which means it has to have positive eigenvalues. You can write that constraint, those two constraints really, as first of all, A, B, B, C. This is the symmetry. Symmetric means B and B are the same number. the positive definiteness constraint is equivalent to these two constraints. One is that the determinant of sigma is greater than 0, and also that either A or C or both are greater than 0. Okay, and if you look at this as a quadratic constraint in ABC space, and then this is just staying on 1/2 of the side of A, the space that satisfies this constraint is a solid cone. So it's the interior of this solid cone. Okay, so covariance matrices live in a solid cone. It's a 3-dimensional subspace of R3. This is A, B, C space. So these 3 numbers, A, B, C. And that cone really is a nonlinear space. If you take straight lines in the cone space, these are not ideal paths to take between points. The information geometry tells us you should take more of these hyperbolic curves, and they have some advantages. One is, as we'll see, the information geometry, the metric works out to make sense with the probability model, but also these curves, notice, they stay in the space. They can go off to infinity and they stay in the cone, whereas if you take a straight line path, you'll at some point hit the edge of the space and run off the end. So there's a natural geometry to the space of covariance matrices that we can work in. And the same thing holds for really any model, is that they have a natural geometry that comes from the information geometry we're going to learn about. Okay, I'm going to stop talking and hand it over to Iman for the last 15 minutes. All right. Oh yeah, yes.
Right, so we covered a lot of theory of manifolds and topology, and which is what we covered through the class. But why do we need to learn all of this in 2023? Mainly because of its applications in AI. So the first application that you see here is in unsupervised learning. All of these different fields in artificial intelligence, what we'll do through class is that we'll cover different areas of AI and latest trends in AI and see what and how it connects to the theory that we learn about manifolds and manifold analysis. So in general, unsupervised learning is essentially just an automatic discovery of intrinsic structure, which essentially is the manifold of the data. So because now we saw that the data lives on a smaller manifold, what happens in unsupervised learning is that you don't have any labels for the data and you sort of automatically try to learn a structure in that manifold in which the data lies. So essentially you're trying to learn what the manifold of that data is. We'll also cover some self-supervised learning. Self-supervised learning, essentially what it does is that it embeds data on a manifold and then sort of compares the data based on similarity using a known metric on that manifold. So there would be, we'll define a manifold which we already know the metric space for, and then we sort of embed all the data on that manifold and sort of do analysis there to see if 2 images are similar or if 2 data points are similar or not similar. We'll look at details about each of this topic in the following slides. I'm just trying to make a connection that everything is about manifold. Okay, graph neural networks. So graph neural networks essentially sort of model data which is represented in graphs. All of the data, most of the data that you see in real world is sort of graphical data. A graph itself, the way it's constructed with its edges and nodes, is automatically a discrete representation of the underlying manifold of the data because it's connected through edges and relationships between 2 data points, and because it spans the whole space but only is connected through edges and nodes, is automatically a representation, a discrete representation of the manifold in this entire space where the data lies. And the last topic that we'll cover is generative modeling. Generative modeling is the most easily connected to manifolds and is the hottest topic these days. So variational autoencoders essentially just learn a manifold as their latent representation and learn a mapping from the real data distribution to the manifold and from the manifold to the real data distribution again. And via navigating this manifold of the latent representation that it has learned, it sort of creates a representation of the manifold of the data. Diffusion models are essentially just nested variational autoencoders, so they also sort of simulate a noising process of images which goes through different manifolds, and each manifold is described differently based on how much noise is present in the data. So we'll look at how diffusion models work as well. Alright, so let's just do a brief overview of what unsupervised learning is and how we'll cover it in this class. Does anyone know already what unsupervised learning entails? Anyone?
Label.
Yeah.
Learn without label.
Yeah, so imagine you have a problem where you have a lot of information about the data points, but you do not really know the information that you want to predict about any of the data points. So you have like, let's say, you go to a jungle and you have a lot of heights and weights of different animals, but you don't know which animal is which, right? So what you do is you essentially sort of cluster these together based on, so this is just a clustering example, it's one of the methods of supervised learning. So you cluster these data points together, things that are closer together sort of represent the mode in that distribution. A mode in the distribution is where most of the data is concentrated around. So by doing something like this, you would already understand what parts of this data space has more data and what are the modes of this underlying manifold are using like a basic unsupervised technique. All right, self-supervised learning. Does anyone know what self-supervised learning is? Okay, so self-supervised learning is essentially when you don't really have labels, but you want to use something like an internal structure in images to sort of learn some information about these images. So essentially in self-supervised learning, the most famous method these days is contrastive learning, which is recently started working. You must have heard of the model called CLIP, which is OpenAI's model. And these models do very well at retrieval tasks. And retrieval tasks are, for example, if you go to Google Photos and you write like a caption, and Google Photos automatically sort of gives you the images that align with that caption. So all of that is happening via contrastive learning. So essentially in contrastive learning, what we do is that we project the data to a known manifold again. This manifold is known, we know what the metric space here is. Essentially, you would represent this as a sphere, and the metric would be like the cosine distance between those two points. So essentially what you do is you project a bunch of these images to that manifold and then sort of compare which images are closer together on that manifold, and using that, using the metric that you already know, you sort of optimize a model to be able to understand these differences and similarities between data points. All right, graph neural networks. So graph essentially, like we talked about, are automatically discrete approximations of continuous manifolds in discretized in a way where the nodes represent what the data is and the connections represent the relationships. So essentially, GNNs, graph neural networks, usually help us characterize the whole manifold by discretely learning an embedded representation of the graphical data. So you can do node predictions, graph predictions, edge predictions, and we look at this in detail in later classes and how it connects to manifold math. The last topic is generative modeling, and we will cover two types of generative models. The first one would be a variation autoencoder. A variation autoencoder is essentially just taking your image from a high-dimensional manifold of images, like we discussed, which can span any number of millions of dimensions, and then project it to a latent space. This latent space will span a lower dimension, and we'll know what the latent space is, so that we can randomly sample from this latent code, and then it will go through a decoder, which projects the latent space back to a high-dimensional manifold of images. So that way you can embed a high-dimensional image into a smaller latent code. So it automatically already works as a data compression mechanism, but you can also randomly sample data points from this latent code and decode images, which means that you can randomly start generating images from scratch. So it becomes like very good generative model, which can generate images from scratch in large numbers. Another type of generative model, which has become really popular these days, is our diffusion models. Diffusion models, essentially what they do is that they take an image, they add a little bit of noise to the image, and they keep adding noise until the image completely becomes noise. So you can imagine this is pure noise, spans a larger number of dimensions in your in the data space, whereas this lies on a smaller manifold. So there are a bunch of manifolds that keep getting increasingly complex as you add noise. So we'll look at how the manifold map functions with this. And you can imagine that once you have a model that can undo this process, like take a noisy image and try to come up with an image which does not have noise in it, you can chain that model to generate images from pure noise. So you can just randomly sample noise and then pass it through that model again and again and again iteratively and come up with an image. So that also functions as a great generative model. Another thing that you can do is that if you condition this reverse process on text, what will happen is that if you give it a caption, the model will try to come up with the image that matches that caption. And these models are and these text condition models have been very popular recently. You must have heard of the Stable Diffusion model and OpenAI DALL-E 2. We'll discuss those models later in class because they've shown how good these diffusion models can get. Yep. Pretty much.
Great, so I think we have a couple minutes left. If anyone has, after all of that whirlwind of topics, anyone has any questions about any of those things for Aman or me?
I have a pretty broad question. Are we planning to go like cover the basics of these topics or will we go paper wise paper and?
So what we'll do is that for each of the topics, I'll give you an overview of what's happening these days, and then we'll cover the latest 2 or 1 papers, which really tell you exactly how the latest models function, so that you have an understanding of the entire field and where it has reached now. In all of those these AI related topics. And also how they are connected to, of course, manifold math and manifold learning.
Back to the CMSLR slide.
This one?
Yes, this one.
Yeah.
So in the paper, what they do is they project this onto a space. They do not talk about manifold at all in the paper.
Yeah. Yeah, so a lot of these things can be looked at from different perspectives of mathematics. Essentially, what contrastive methods do is they try to sort of maximize the mutual information between the data that you seem to be paired and the data that is unpaired. So how they do it is via projecting it to a space and then sort of measuring a distance there. Because why do you project it to a specific space is because you already know the metric there and are able to compute cosine similarity very cheaply, which is how it connects to manifold math as well.
How is the self-supervised learning different from unsupervised? Because even in unsupervised, you do check the distance between the centroid and then.
Correct. It's that's a fair point, but it's a very terminology related thing. Like initially when unsupervised learning came about, the methods were what they were trying to do was sort of embed data into a low dimensional space and sort of recover the data from it, and essentially was trying to compress the data into a smaller latent code. But later when self-supervised learning came out, the paradigm was so different, they sort of wanted a new name for it, which is why self-supervised learning became a thing, because the model sort of supervises itself by using 2 different copies of the same model or 2 different copies of the same image to sort of contain the same information. So it's just a terminology thing, but yeah, even self-supervised learning is done without labels.
Okay, great. So that takes us right to the end of the time. We'll see everybody on Thursday. Thanks.
They're gonna